All right, just getting started on um, week two of our computer vision. So I wanted to start just to kind of take a quick poll and understand like where people are at in terms of did you spend some time watching the videos? Did you spend some time looking at slides? Did you do any like look at the material? So just kind of raise of hands, how many of you spent some time watching the YouTube videos, looking at the slides, playing with the notebooks? We have a couple. Okay. Okay. So if that's the case, what I want to do is I will put the slides on Slack and I can give everyone like 10 minutes just to gloss over them. And then after that, we can kind of guide based on that because I think it's more useful if people at least have like their bearings on what we're looking at. So I'm going to put the slides in the Slack and then maybe I can also put links in the Zoom for everyone online. So they they talked about here's what a human sees, here's what the machine is actually seeing. So the machine is just seeing a bunch of numbers here. So that's slightly different from the way that we perceive things. And so with all of this stuff that we'll be working with, often it's convolution, sometimes it's transformers, but in general, there's something that is looking at those numbers and then finding some pattern there. So you can have CNN or some other kind of network that's going to learn based on the patterns that it sees in these numbers. Um, so they made a distinction of a couple different kinds of what they call discriminative computer vision versus generative computer vision. So we'll start with the discriminative side. So discriminative is like something like classification. So it's saying like what objects are in this box. So it says there's a person here, there's sheep, there's a dog. You might even go more granular and say like there's grass, there's a hill, there's whatever. You might have a bunch of different classes and you just look at an image and say, does something exist in that image or not? And then you have a level more granular than that, which is object detection. So saying not only is there an object in this frame or not, but where is it? So it's drawing these boxes around the sheep, around the person, around the dog. Um, and then even more granular than that is saying pixel by pixel, I want to classify every instance of something. So you want to be able to specifically say this is exactly all of the pixels for this one sheep. Here's all of the pixels for the other sheep. Here's all of the pixels that we can see for the person. So you can see this is much more granular than the object detection saying just here's a box, the thing is inside of there. So this is saying for the exact pixels, focus in on what the object actually takes up. Um, so you can do stuff like this where you're actually doing both. So you're saying, look within this box, and then more precisely and granularly say what all of the pixels are. And so the flip side of the discriminative is the generative. So this is what a lot of people are interested in nowadays. So you can plug in some text. You can say, make an image of this, do a horse riding on a cowboy or something impossible, and then it will just make an image for you. Um, so this is a big field now, but is relatively recent. So you can make images of people, you can make new satellite imagery. And so people have done various things in order to merge these together. So you can combine generative and discriminative. So you say, I have this data set. Some of these are healthy brains, some of these are unhealthy brains. And then you go and you say, generate more unhealthy brains, because I don't have very many examples of those. And then you can train a discriminative model on top of that, saying, now I have these fake generated brains, go treat those all as negative, and then you have a new synthetic data set that's been just created rather than go find more go find more unhealthy brains. Um, so any questions, discriminative, generative? Yeah. Yeah, yeah. So the question was like, don't you get bottlenecked by the data that you have and the label? So like you can't generate better data than you already had, basically. Um, my experience, so there are papers where they have successfully done it, but my experience is that it never works. Like you generate samples and it's going to generate things of the same quality that you were already trying to classify between. So whatever the generator learns is going to be the same that the discriminator learns. So there are examples where it has worked, but my opinion is that that typically doesn't. Yeah. Um, so after that, they were talking about the um, how images are actually represented with the common libraries. So they walked through uh, Pill and NumPy. So one of the things that they were talking about is that the images are represented by these uint8. So these are values that can go from 0 to 255. Um, and so the way they represent this, it fits in a single byte. So you can say this bit represents 128, and then you say how many of these are on and off represents the 0 to 255 value. So 0 is black, 255 is white. And so that's how you make up all of those pixels that we were seeing. So we saw the RGB word values that were 34, 27, all of those different things. So that's the way that this data is typically packed. So one of the things that I want to highlight here is it's typically there's a different format that is good for like storage and memory versus what you're computing with. Um, so for storage and like efficient representation, most people use this uint8, but then we'll see later when we swap to floats and what the value is there. Um, so we can see this is a grayscale image and this is a 3, and we see most of these values are 0, and then some of the values are higher than that, and that becomes gray and then white at the corners. Um, and so that was a grayscale image. Scaling it up to RGB, this is kind of the example we were looking at earlier. So we have this image, and then we see the stacks of here's the blue, green, red channel, and then we can see the values in each of them. So we say for this specific pixel, it has 19 red, 7 green, 6 blue. And that's what makes up the color that we actually see. So it's a merging between all of those. Um, so then getting into the pillow stuff. Um, so here's how you open an image. You point it to a JPEG or PNG or some other file format, and then it will just open it up. And then you can inspect what mode is it in. We know that this is from the MNIST dataset and it's grayscale, so it's going to tell us L, which means grayscale. I don't know exactly why it's L, but and then we can look at the size, and so this will tell us what's the height and width, and then we can convert from pill to numpy. So when it's pill, it's like kind of just stored it in its own format saying this is an image, and then when you actually go uh or this is saying you can read from it, sorry. So you can go from a numpy array and say pack this into an image, and then you can do all of those operations on top of it. So you can switch it to grayscale to RGB to rotation to a bunch of different stuff. And then you can save it back out to PNG, for example. And then you can visualize it with something like matplotlib. And so this will make it in a format that is good for us to consume. It's not just the raw numbers anymore. Any questions there? So then going to NumPy arrays. So this is what I was saying before. So you have like that pill format. It opens the image, but then you can actually pack it into a NumPy array, and NumPy arrays are nice because you can do basically any linear algebra operation on top of it. So you can do something like, say, invert it. So originally it was black background with white text. Now we can make it white background with black text with something like just saying do 255 minus all of the values, and then it flips everything because it's saying you start with 255 and then you cut the pieces away from it, and then it inverts it. So you end up with this image here. So that was a simple grayscale example. Now we have one that is RGB. So it becomes a little bit more complicated when we have multiple channels now. So we have things represented as this array saying we have the top left has a red pixel, the middle is green pixel, the bottom right is a blue pixel, and then we can see they've overlaid other patterns on top of this. So this is saying like each of the pixels actually have different proportions of things. And then what you can do is you can go and actually merge that or visualize specific parts of it. So the way the indexing works on the NumPy arrays, this is always like very confusing part. So you have to think about it as the first axis is height, and it's flipped from what you probably expect. So in like typical graphing or something, you say this is 0, 0, and then to the one direction is up, and the other direction is up on the y-axis. It's actually flipped. So the y is down and the x is to the right. So if you start at 0, 0, you're actually in the top left corner. So if you're trying to index these, you have to remember that if you go up on the first axes, you're actually going down in the image.
Hey, Ryan, quick comment. There's different packages that have the dimensions, height, and width, and later we'll see the other ones in different orders. But I think everything in computer vision always starts in the upper left corner. It never starts in the lower left the way that, like, when you're taught algebra or whatever.
Yeah. Yeah. Your regular graph coordinates.
Yeah.
Yeah. Yeah. So this is looking how we index in and say, look at this specific channel. So this is saying grab all of the height, all of the width, but only grab the red channel, all of the height, all of the width, but only grab the green channel, all of the height, all of the width, only grab the blue channel. And then we can look at those individually so we can see how much red is there, how much green is there, how much blue is there. We view that as grayscale individually, and we can see what each of them looks like. So the first one was saying look at it as grayscale. This one is saying now we can apply a color map, and then it's saying look at it as red, green, blue again. So that's a simple thing that we can do with matplotlib. Just say here's our color map. So when it goes up in value, it's more red. When it goes down in value, it's more white, for example, or black. So there's a bunch of different color maps that you can apply. This is just a good one for saying, look at all of the channels individually. So here's an example they were showing where we can kind of do manipulations of the NumPy array, and then we can go visualize what we actually did. So this is saying we can draw some rectangles or squares on top of the image. So we say for this region on the y-axis, this region on the x-axis, set it all to 255 on the red channel. And then for this one, we do a different region of the green, different region of the blue, and we set those all to 255. And so that's what yields this overlapping region of we turned red on from this section to this section, and we turned green on from this section to that section, and blue from this section to that section. And then we see the regions where they actually overlap. And because we did the image.merge, it's adding all of these together, and then we get this sort of blended image where we see all of the overlaps. So just to Ted's point earlier, like the formats are different between all of the different stuff that you'll be looking at. So some of them might have height first, some of them might have width first, some of them might have channels first. It's all topsy-turvy. You have to keep track of which format you're in and which one is the different axes. So just something to be very careful of. So NumPy will default to having it height, width, channels, and then pill will actually have it alternate. So it will have width and height. So you have to be careful if you're trying to go between the two formats. You might end up with something that's transposed. Um, so we did NumPy, we did pill. Now going on to PyTorch. This is very, very similar to NumPy, but the major benefits with this one is that you can do this, all of these storage and operations, all of the math, you can do it on GPUs or TPU. So NumPy is specific to just CPU. And so this is very, very powerful for certain operations that you might want to do on images, where you say my GPU has 16,000 cores, my CPU has 4. And so you can say apply this operation to every pixel of an image or something like that. And the other major benefit of PyTorch is its automatic gradient computation, autograd. And so what this does is it helps us train neural networks. So it lets us keep track of, we did this operation, what's the derivative, and then how do we need to update a neural network in order to actually train a model with that information. So like I was saying, the CPUs versus GPUs very good for all of the graphical stuff. You have lots of pixels, you want to apply the same operation to all of them. CPU, very general purpose, but you can't do certain things as fast with them. So one thing to be careful with the PyTorch stuff is that you need to make sure that your data and model and whatever you're doing is always on the same device when you're trying to do operations between them. It won't just automatically transfer for you. So if you have something that's on CPU, for example, so you have your image, it's on CPU, you go try to do some model that you loaded onto the GPU, you need to do an operation in order to shift them, in order to make it happen in the same place. So this is like a extremely common line that you will see in pretty much everyone's code, just saying like, if I have a GPU, make that the default device. If I don't, put it on CPU and just do the things manually. So this is saying, let's define a linear layer and let's make it 28 by 28 because these MNIST images are 28 by 28. They're very tiny little snippets. And then our output features are 10. So this is the number of different numbers that we're classifying. So we're doing 0 through 9. So it's saying load the model to GPU, put our image on GPU, and then we can pass the image into the model. And then the model will output something saying, I think 0.7, it's a 3 or something like that. So one of the things that you have to be careful about is most things assume that your data and model and everything is going to be on CPU. So if you want to save it to some other format or visualize it or anything of that nature, you need to move it back to CPU. So what they're trying to show here is basically I took my model, I made some outputs, and then I want to visualize them. It won't be able to visualize this because this is still on GPU and you need it on CPU in order to actually plot it. So they're showing if you move it to CPU first and then you plot it, then it works perfectly fine. So they highlighted some of the benefits of doing these things on GPUs. In many cases, it's just like not even an option to do certain things on CPU. Like you go and you try and apply it and you say it takes 3 minutes to process one image versus a third of a second or something like that. So I think that these are even kind of understated because it's just a single matrix multiplication. But if you have multiple of these cascading, then you say this single layer took 4 seconds, the next layer took 5 seconds, the next layer took 3 seconds. So all of these things might stack up if you have multiple different computations going on. So they're showing this 32 by 32. It can complete it basically instantly. Like this is so quick that it doesn't make any difference. But when you start scaling up and you have bigger matrices, so it's entirely possible for you to have an image that's 2048 by 2048. a CPU can probably do it decently fast, but a GPU can do it order of magnitude faster. And then when you start getting bigger and bigger, the lead becomes even more pronounced. So you end up with something that could take like 4 seconds. Um, so talking to the autograd portion for a second. So very important to all model training is understanding the you need gradient descent in order to improve these models. And so typically what you have to do is you have to actually compute the gradients and then move down the direction that you're trying to go in order to move the model better. So this is all automatically done by PyTorch. You don't have to do your own derivatives and gradients and all of the math. You can basically just say like, multiply this by that. How do I change this in order to improve the performance of the loss in some way? So PyTorch hides a lot of the details for you. You don't have to be super in the weeds on how do I take the derivative of this convolution operation or some matrix multiply thing. It does a lot of the details for you. So then they started digging into the autograd portion. So one of the things that they were highlighting is that you need to turn gradients on and off when it's appropriate. So what I was mentioning is by default, it will track a lot of these gradients. So it will say, I did this operation, then that operation, and it changed the image in some certain way. Sometimes you might not want that because it's just a waste of memory and you're just accumulating things as you're doing operations. And other times it's actually critical. You need that for your training operation. So they're showing basically we have this weight, we have a X1 input, and then we have Y, which is our target. And we're saying multiply our weight times our input. And then what's the difference between our prediction, which would be this portion, and our output. So it's saying make a guess of this person's age and then measure how far away it is from the correct answer. And then at the end, we're probably going to want to update the weights in order to make that guess more correct. So we're moving in the direction of minimizing the loss every step that we take. Any questions on the autograd part? Yeah. 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 So it's going to keep track of all of the operations that were applied to that tensor. And then when you try to, it will basically, if we look on the right hand side, this is saying, okay, we have weight one, we're doing some multiplication, we're doing some subtraction, we're doing the absolute value sign. So we can see the path that the weight one went through. So it said this had some interaction with X, it had some interaction with Y, and then we're taking the absolute value there. And so we see all of the stuff that it went through. And so along the way, it's saying, okay, you applied this, and then you applied this, and then you applied this, and it made this final outcome. Measure how correct, how incorrect it is, and then take a movement in that way. So I in my PyTorch usage, I typically haven't had to set this because I just default it to on. I just say whatever I'm doing, allow it. And then a lot of the layers will automatically have this set. So most people will use in Torch, there's a neural network section, and all of those will have kind of the defaults and correct things preset. But yeah, it's storing copies of all of the stuff along the way, all of the operations. It's saying, here's the path through the graph that we took.
If I could add a little color. So a lot of times if you're using packages, so if you just say, hey, I went to Hugging Face and I pulled a small llama model or whatever, all of this is handled for you behind the scenes. So you don't need to do it that often. But I think it's good to understand some of the fundamentals. So underneath the hood, if you say, here's a tensor and it's this shape, this many floating point numbers, and you say requires grad equals false, then basically all it does is allocate memory for those floating point numbers. If you don't, and the default is true, then it's also allocating some space for where it's going to store those gradients. Um, I don't know exactly all the details, but then there's even more space that gets allocated more dynamically. When you do the calculations, it has to keep track of all the calculations and intermediate values so that ultimately later on you can get the gradients and do things. So it's even more expensive if you let it do the gradient calculations than just simply to say requires grad equals true. That's a lesser thing. So you don't necessarily run into this if you're just using a bunch of packages, pre-made models, but let's say you added a tiny bit of code where you wanted to keep track of some progress thing, how many images it got right or wrong or whatever, then that's where typically you would say requires grad equals false just to be a little bit cleaner.
Yeah, and one thing I'll point out here too is they turned off the requires grad on the input, so we don't care about tracking how the input was changed. We care about the weights. The weights are the part that we're keeping track of and saying update this in order to make the model better, because we can't change the inputs. We can't make the inputs better. And the same thing with the outputs. We can't change the output. So we just say don't care about the inputs or the outputs, only care about the model, because that's the part we have control of and can modify in order to make this loss function smaller. Um, so similar to the other formats, we were looking at pill and numpy, and now looking at torch, we have another format in the mix. So the way that people typically format things is they will have n is your batch size. So often in neural networks, we're doing batches of images at a time. So we might do 16 images or something like that. So we have batch first, and then we have channels, height, width. Um, and so just to be clear, this is different from the NumPy expectation. So NumPy expected height, width, channels. This is batch, channels, height, width. So even if you break off the batch piece, this is still flipped. And so this can be extra confusing because even within PyTorch, different models might have different expectations. So you might have to transpose things around and make sure that you're doing things in the correct order. And most of the time, you will just hit an error immediately. You just say, try to pass it to the network, and it just says, this is the wrong shape. So typically, it's not that big of a problem. It's not going to silently like train a model based on the channels or something. So just you have to be careful when you're doing these operations, especially swapping between NumPy, PyTorch, pill, anything else. Um, so that's what they were focusing in on here. So they were basically saying, here's a transform. So there's the PyTorch transforms, and there's the Torch Vision transforms, or there's whole packages focused on these transformations. And so they're saying this is one that you can use in order to swap between NumPy format and Torch format. In practice, I haven't used this very much because typically I want to do it by hand just to know that I'm doing it in the correct way for my specific model, because it's not guaranteed to be true that your model is expecting channels first or channels last. And that's something that can be just handled randomly. Like I don't feel like this standard is that strong for that. So here's some function that you can use. In general, I would say it's easy enough to just say transpose and then flip them around in whatever direction you want. So like they're showing you can do this permute, and it's basically saying swap the axes in various different ways. This is the way that I typically do it. And I'll just kind of have an annotation saying like, okay, I was channels height width, now I'm height width channels. And that helps me keep track of things as I'm doing all the different options. Um, so along with that, the plotting can be annoying. So the same thing, if you swap the axes and then you try to plot something, you might end up with something that is like, this is a 3 pixel height, but it has whatever, a ton of channels and stuff. So you have to be careful with that when you're plotting as well. So you might have a different format for NumPy, different format for PyTorch, and then you might have a different format that you need for plotting. So it's a bit difficult to keep track of all of those. Um, so digging into the what I was mentioning earlier, you might have different formats for storage and visualization versus what's good for training. So typically for storage, we store things as those uint8s that we were looking at before, but in reality, most neural network training prefers you to be at a mean of 0 with a standard deviation of 1. And so all of these architectures are built with this sort of assumption in mind. And so um, one thing that we typically do is we say this uint8 is 0 to 255. That's not really that great of a format for training in. And so what we'll do is some people will say divided by the mean, or subtract the mean and divide by the standard deviation, or more simply, what a lot of people do is just divide it by 255. So you know that my pixel values are 0 to 255. If I divide it by 255, then all of a sudden it becomes 0 and 1, and it behaves well for a lot of the things that we want to do with it. So one of the things that they're mentioning is like even the softmax function or various exponentials will just blow up if you pass in 255 to it. So if we do this very simply and we just say divide it by 255, now the max value is just 1, and then you do e to the 1 or whatever you're trying to do, and it's not going to be some ridiculous value that just blows up. So they're showing basically if we divide by 255, it makes things easy, and then you can do all your neural network training and computation in that format, and you don't really have to worry too much about numerical stability. So if you do it 0 to 255, you have your 255 value, and then it just becomes something crazy. And then the biggest problem is just running out of digits to even keep track of things. So this is showing like here's the original 0 to 255, here's just divided by 255, and we get this simple transformation that has a different scale, but it's exactly the same information. One thing to note about this is switching from uint8 to float 32 or anything else, you're actually consuming a lot more memory now because you have to have extra bits for the storage of the float 32 versus the uint8. So there might be some world where we just say we have unlimited storage, we have unlimited memory, just always store everything as float 32s, but in reality the uint8 is so much more efficient for most things, so we tend to do it in that format.
Just another quick comment. I think in Python, generally, you can be pretty lazy. So you can just like divide two integers and you'll get a floating point number as a result. But in PyTorch, when you're on the GPU, generally you don't get all this kind of like automatic casting and stuff because there's overhead associated with all this automatic stuff. So instead, in order for it to be fast, everything tends to be explicit. So you really need to convert things to floating point before you do math with things. Generally speaking, on the GPU, you cannot do math on integers. Yeah. Yeah, so the question's about quantized. So obviously there are floating point quantizations that take less space. But if you're using integer eights, unsigned integers, then yes, what they're doing is they're specifically doing only, I think, addition, subtraction, multiplication. They're not doing division with those integers, and then they're using the integer cores instead of the floating point cores. And I'm not like a chip designer or whatever, but I think ultimately, if you think about it, the on the chip, how much you can optimize it is partially dependent on just how big the data is, right? So if you have 16 or 32 bits, that's how many whatever lines of input you need to squeeze into this operation, and then how many additional lines of output. And so if you have 8x8, it can just be a much smaller area on the chip and ultimately faster and less power.
Yeah, and there's some like a lot of people use mixed precision. So there's even like even if you have floating point inputs, you can have different levels of precision. So you can say do it at float 32, do it at float 8. People are going all the way down to FP4 now. So you can have different levels of precision, and people have gotten very fancy with how they do their reduction. So they're like saying, I do it with this and a mantissa of 3, and they're doing all kinds of crazy stuff now, trying to reduce it and say, we need a wide range of values, but we also need granular values, but we also want to ditch as much of this as we possibly can. So people have been getting very fancy with that and saying like, how much do we actually lose when we reduce the precision in various different ways? Um, so partially it's like, how do we reduce memory usage? Part of it is how do we do things faster? How do we do it without losing any performance? Because typically when you go down and down, you're losing some value once you're like at the limit. Not Not really at higher levels. So, like, if you do something at float 32, you don't expect it to be better at float 64 because it already has such tiny little increments and so much range that it doesn't need any more. But at the flip side, when you're saying reduce it from float 32 down to float 4, then you're losing so much precision that it's like there's accumulated like rounding errors within the network basically. But most people doing stuff at float 32, float 16, there's no extra value from more precision, for example.
Yeah, I think it's a good question. And so the short answer is probably no, you don't get a better model with higher precision. It's either it works or it fails. So if you have a lot of overflows and underflows while you're training, then you just get junk. So basically, it's like on any given model with whatever data, it's like, yes, I did float 32 and it worked. I did float 16 and it worked. I did float 8, it worked. At some point, then I just got garbage. It's not like it's slightly worse, it's just completely garbage.
Okay. Um, I'll move us on to the second section. Did anyone have any questions that they wanted to lead on from the second section? Okay. Um, So going into the first section, it's now we understand how to represent the images. How do we pass them to a model? What do we do with that? So the first section is focusing on predicting car prices. So imagine you have this image of a car and you want to build a model that says, okay, look at this image. Is it a nice car? Should it be $100,000? Is it a crappy car? Is it 3K? Um, so you can probably do some evaluation based on these images. Um, and so we see like the Lamborghini down here is 225K, and this Dodge Caliber wagon next to it is 4K, for example. And so we're trying to train a model that actually looks at the image and kind of grades the quality of the car and then makes some distinction there. Um, so this is showing a plot saying we had some initial model that basically said, look at this image. Um, here's the actual sale price of the car. Here's the prediction of the model. It was only off by $300. That's pretty good. Um, and so now we'll look at like how do you create something like that. So the focus is just understanding neural networks, understanding the inputs, the outputs, the hidden layers, all of this stuff in between. So they started by looking at artificial neural networks. So this the neural network systems took inspiration from real neural networks. So real neural networks, you have these dendrites that receive signal from somewhere, and then it gets sort of processed in the middle, and it decides, am I going to fire off some signal to the next neuron or not? And so this is kind of the inspiration of the artificial neural networks that we've created. They actually function pretty differently. There are people that are researching spiking neural networks, which is a totally different field, but we still call them neural networks, even though they operate significantly differently. So a basic model is called the perceptron, or you might know it by MLP or many different names. So imagine we have these sets of inputs. So we have X1, X2, however many inputs that there can be, and then you have a weight matrix that is learned, and then that tells us what the final output is. So it's doing some matrix multiplication on top of these inputs in order to make some final output. So like in our case, we're looking at the pixels, we're saying do some math on it, and then give us a final number at the end. So they're showing kind of the makeup of a regular fully connected layer. So we have our inputs, we have our weights. The weights are being multiplied by the inputs and then summed together. And then we have some activation function. So one of the important things about neural networks is we need nonlinearities throughout the network in order to make these really complicated patterns that we're showing. So you could do just a stack of these weights, but if you did all of these on top of each other without any non-linearity in between, then you just end up with a linear output. And then there wasn't really much reason to have all the layers in the first place. So the activation functions are actually very critical. That's what makes us build these systems that are so smart. They're not just linear shifts on top of the inputs. They can actually discover patterns. So the way that these are trained is you have some target value. So let's say this car is 84K euros or very, very close to it. And the model says, okay, here's my prediction. And then what we do is we measure how far was that from the truth. So this was only €1 off from the correct answer. And then we could say that's a very good prediction, but we want to make it even better. So push it in the direction of making that value lower. So then we might take a step and we say, change this neuron to be a little bit higher. So it just reduces the price by $1 or something like that. So that's generally the way that these systems work is you pass some inputs, it makes a prediction, and then you're trying to adjust the model in order to make that prediction closer to the truth. So one of the things that they point out is that these images are very high depth. So imagine you have a 1080p image. It's actually millions and millions of pixels. And so if you wanted to pass that to your input layer, you can't have an input size that's a million. It would be learning every single pixel. So if this image was shifted one pixel to the right, one pixel to the left, it has to learn that pattern entirely anew. So here's a simple MLP like we've seen in the past few slides, but now what they've done is they've added a hidden layer. So this is taking some input, it's doing some transform, it's doing some nonlinearity, and then we're ending up with the hidden layer, which is some different representation, and then it's going out to the output layer after. So now this has one more layer than we were looking at before. So in the previous section, we had the small brief on just like the gradient descent updates. So this is saying we have some weight, Wij, and then we know what the gradient is. We're saying if we push this up in some way, if we push this down in some way, it's going to change the loss function. We're trying to make the loss go down. So we have a learning rate that's saying take a tiny little step in the right direction. So these systems always function iteratively. So it's just taking little baby steps towards better and better answers. And you're going to expose it to the images repeatedly in order to push towards the the minima when the model's more accurate. Um, so in the first one, we were looking at mean absolute error, which is one of the common loss functions. So you need some way in order to grade, is the model good, is the model bad, and how do we what number do we minimize in order to get better performance? And so mean absolute error is a good one for regression. So it's basically saying what's the distance between the prediction and the actual label, and then just absolute value of it. So we don't care if it was over predicted or under predicted. We just care how far away it was. So other things might do the mean squared error, or they might do the root mean squared error, or some other function. But mean absolute error is a common one. For classification, you might do something like cross entropy. So if you were classifying here, so instead of guessing the price, if you're trying to guess this is a BMW, this is a Honda, for example, you might have a bunch of different classes. So you would have a different loss function. So you define it in a different way because you're doing a different task. So in these neural networks, we have a bunch of matrix multiplication. So what I've been saying is like we have the inputs, we do a matrix multiply with the weights, and then that gives us some final output. So if you have multiple layers, then you're doing multiple matrix multiplies or to get through all the layers, and then you get all the way to the end and you get some output. So now looking at the dimensions of things, understanding how many inputs and how many outputs are there. So this is saying P equals 4. P is our number of neurons in our hidden layer. And then this is the number of inputs that we have. So we have N equals 3. So we have 3 inputs. We have 4 hidden layers. So it's going from 3 values up to 4 values all the way down to 1 value. So that's the size of the matrices that we need to have. We need one matrix that goes from 3 to 4, and then we need another matrix that goes from 4 down to 1. So that's an important concept is understanding the shape of your weights and how that's changing the size of your layers throughout.
A super quick comment. One of the things I sometimes have difficulty remembering is, okay, so that matrix is going to have a dimension 4 and a dimension 3. Is it 4 by 3 or is it 3 by 4? And honestly, like I don't get it right 100% of the time. But in most of deep learning, you're going to see that the input vectors are on the right and the weight matrices are on the left. So it's always matrix A times vector X. Okay. So I think that's, I don't know, is that left multiplying, right multiplying? I don't know. That's the part where I get tripped up. But that's pretty uniform. There's some rare exceptions. But in case you're ever like kind of down in the guts, you know, figuring out what's rows, what's columns.
Yeah. When I was first learning, I was doing the Coursera course. There's an Andrew Ng course that I feel like a lot of people have done. And that was like the majority of the exercises was just, I'm trying to multiply this by that, and the shape is not right. How do I fix this? And so it was a lot of like, okay, transpose. Okay, this needs to be a different size. This needs to be a different size. So it's not something that I do that often anymore because a lot of things are just kind of automatically handled by layers or keras or something else now, or the network is already defined. But I do think that it's valuable to understand like when something is breaking, is it because I transpose something, or is it because the layers are not the correct shape or something like that? It's very valuable for debugging just to understand like what the expectations are. So moving on to this slide, I mentioned like if you have multiple layers and you don't have a nonlinearity, you're going to end up with a simple boundary like this. So this is showing a single layer going from inputs to outputs and saying this is the most complex representation we can make. But then if you look at this one, we add in another another layer, and this can make a much more complex shape. So this is just the most complex relationship it can define. So it draws these little triangle trapezoids saying, here's where I think the blue are, here's where I think the yellow are, here's where I think the red are, but it just cannot do any better than that. So if you add in another layer, or if you add in more layers, then you can go more and more complex relationships. So you can see in this one now, it's more correctly defined. Here's this like squiggly region in order to capture all of the blues. Here's to capture all the reds, all the yellows, for example. Um, so when I talk about neural networks, I'll typically say like the expressiveness of the network or something like that. This is what I'm thinking of when I say that, is like, is it able to draw the lines that I need? Does it have enough neurons? Does it have enough layers? Does it have the right configuration to represent the relationship that I'm trying to find? Um, yeah, but it's very related, yeah. So more layers lets it understand deeper and deeper about the language. So if you have a very shallow network, it might only be able to say, look at the previous word or look at the previous few words and the relationships between them. But if you have more layers, then it can say, do all of this complicated combination of, I know something about Barack Obama and I know he was born here, and then do some combination there. So when you're doing more layers, you're getting this like higher and higher levels of freedom. So it can kind of learn all of those different patterns. Um, so now talking about validating and testing the model. So this is something that we talked about a lot at the last case study. So it's very, very important to always have a separate set that you measure your performance on. So we can see in something like this, it makes these nice curves and it perfectly captures all of the data. But then if you say, plug in some new realistic data, is it going to represent in the same way? Is it going to be able to do predictions on new data? And that's the most important thing with basically any model, is, are we able to predict on new data well? And so this concept of validation and testing, basically the way that things typically work is you have a training set and you say, this is what I'm going to learn from. And then you have a separate set that has no overlap with the training set. And you say, how does it do on this new set of data? And then you say, whatever I'm doing, I'm trying to optimize my model. I'm trying to get it better on this unseen data. I'm not trying to get better on the training data. So that's a mistake I see some people fall into, is they say, oh, look, I got something perfect. It looks like this. But then you go apply it to some new data and it's not actually well generalized. So this is a very important concept of understanding. Like, you want to set aside some data in order to measure your performance against. And the pattern that a lot of people follow is they will say, I have a training set. That's what I learned from. I have a validation set. That's what I measure my performance initially on and I try to optimize against. And then they have a third set that they call the test set. And that's like never seen, never optimized for. And then they say, if I'm only optimizing my validation set, do I also get good performance on my test set? Um, so talking about gradient descent, we talked about the loss function. So you measure how good is my model at all of these different places. For certain things that are very simple, we can kind of visualize the whole space. So this plot is showing, as you change weight 1 and weight 2, how does the loss change? So should the weight 1 be higher or lower? Should the weight 2 be higher or lower? What's the value that minimizes the loss? What makes the prediction as close to the correct answer as possible? Um, so we can do this in 2D or 3D, but it's much, much harder when you have 1,000 neurons and multiple layers and all of this stuff. So it's possible for us to look at this and just say, oh, it's easy, just grab the lowest value, but it's impossible when we say there's higher dimensions and we can't fundamentally see it. So what we typically do during this training process is we say we start at a random point and then we kind of just look around and say, go in the direction of lower, lower, lower. And we hope that we find the basin of the lowest point. So here is the plot showing the training versus the validation loss. So this is the training mean absolute error. So this is showing as it's learning, it's getting closer, closer, closer to the correct answer. So for the training set, we expect that to basically just go down directly every time. So all of its passes of the data, it's learning a little bit more about its training set and it's getting lower and lower values. But then eventually it starts just memorizing features of the data set. And so on the training set, it's saying, I know I saw this car, it was red in this exact pixel. So every time I see a red pixel in this spot, I'm going to guess $30,000. And so it starts learning things that aren't the true underlying pattern. It's not learning anymore. This is a nice car because it has a certain kind of paint or something like that. It's just learning there's a red value in this specific pixel. And then we see that the validation loss starts going up because it's learning those bad patterns instead of the general patterns anymore. Um, so this is a very common pattern that you will see is basically training loss goes down, 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 validation loss goes down, and then after a while it starts going back up. Um, so this is different if you have a massive data set or if you have a very simple model or something like that. Your loss curves can look different, but this is a pretty common one. You say I learned and then eventually I diverge. Yeah, go ahead. Yeah, yeah. So the question was there's a relationship between the amount of parameters of the model and the size of your data set. So the difficult thing is very often we have models that have a million parameters and then you have 1,000 images or something like that. And so in theory, you could just swap one neuron for every one and you've just memorized every single example. We're very lucky that neural networks learn in a way that they tend to end up generalized. So it will find common patterns, but we do end up with a problem where you end up just kind of memorizing past a certain point. So your model keeps adjusting, keeps trying to get the perfect prediction. Like even us looking at a car, you might say that's 20K, 21K, I don't know, it's somewhere in there. But your model is going to keep getting pressured to get closer and closer and closer to the correct answer. And so that pressure eventually is going to make it memorize the specific factors instead of like actually learning, okay, it's roughly in that ballpark and learning, okay, this is a Honda Civic, so it should be kind of in this range, but there's a bunch of factors in there that you can't properly represent. We don't know the condition of the brakes or any stuff like that. And so the over parameterization eventually will say just find whatever little signal I can, even if it's not like the true reason of the price being fluctuated in some way.
So Ryan, I don't know if you saw, there's a question in the chat. What if you don't get that action? What if your training loss doesn't go down? You want to briefly?
Yeah. Yeah. There's a million different situations that you can hit for everything. So if your training loss isn't going down, then what the general wisdom is that your model doesn't have enough capacity to learn your data. So that's a common troubleshooting thing that people will do is basically say, give my model a ton of capacity. Does it learn the data at all? Does the training loss go down? If it doesn't, then probably something's wrong. Maybe it's something wrong with the um, normalization. So, like we were talking about earlier, you have images that are 0 to 255. If you have some input that's on the scale of 0 to 1 million or something like that, and then you pass it straight into the model, it might just break it and it just flatlines or something like that. So it's difficult to say for certain, but in most cases, you should expect the training loss to go down if you have a decent representation, if you have a model with enough capacity. Some things are just incredibly difficult to predict, so it might just converge very, very slowly. So like some people doing stuff on the stock market, for example, having even a 51% accuracy is very, very, very good. So you might see something where you say it's not learning, but it just takes a very long time for it to even get any amount of an edge. Um, so yeah, there's many different things that could cause a training loss not to go down, but in general, the big thing is just to make sure that you have the data in the right format and you have a model with enough capacity, and then you should see your training loss go down. Um, so they have this XKCD comic in here. They have a bunch of good ones on there. So now going into the actual code for the MLP for this regression task, they're talking about the details of the PyTorch now. So looking at the linear layers, looking at the way you can kind of wrap things sequentially and build up your actual neural network. Um, so here's this network that we've been looking at for the past few slides, and then we've also got the code next to it. So this is showing we've got our linear layer that's going from 3 features out to 4 features. So the way that I look at this is I say basically this linear layer is this like web in the middle. That's the way that I think of it, is basically saying, okay, we need three or four out weights for every in weight. So the way I look at this is saying basically, okay, this linear layer is going from these 3 to these 4, and that's how it's created. And then this is going from 4 to 1, so it's saying 1, 2, 3, 4. And in this case, they're setting the bias to false. You could set the bias to true easily. One of the nice things that you can do with PyTorch is it's a little bit annoying to say, I'm going to define all of these layers, and then I'm going to pass the input from this layer to that layer to that layer to that layer, and doing all of it manually. So one of the nice things that you can do is this nn.sequential will basically say, just whenever you're doing something, just automatically pass it through all of these layers in sequence. I know that it's going to just go from here to there to there. So you can just wrap it with this sequential, and then you don't have to manually define like this into that and then into that. So it's just kind of a saving measure, so you don't have to do everything manually. So they define some input data. It's just 1, 2, 3, and then they're saying we can pass this through the model, and then the target is going to be 11, and then we define some loss function, and then we say how close are we to the value with our prediction. So then digging into what's actually happening inside of the linear layer. So we had that layer that was saying take 4 inputs, make 1 output. It's made up by parameters inside of it. So inside of this, we see the shapes. So we know it has a weight of some certain size. So this is just a torch tensor that's saying hold some values in this size. And then we can look at the actual specific values inside of it. We can see that the linear layer also has a bias term. So here's everything that we're looking at here. So one of the things that they were showing was you can do this with bias, without bias, and how does that impact things? So this is showing that the training loss curve, when you do it with no bias, it goes down to some value, and then it caps out and says, this is the best that I can do. When you add the bias term, it allows it to get even closer to the correct answer. So what they're really showing is that on this plot, the red curve is the one with bias. It's able to shift its predictions up and down. The one without bias, the one with no bias, is able to change its slope, but it's not able to change up and down. So it's locked at the origin and just saying change the slope until it's the optimal value. With bias, it's saying, okay, change the slope, but also change the intercept.
And just to be super clear, this is a toy example. So it's not like if you run across Llama 3 and there's a layer with no bias that they like are idiots. It's just for this one toy example with bias works better.
Yeah. Yeah. So they're just showing for a single linear layer with bias, without bias, what's happening. But yeah, most networks are more complicated, and so the actual bias value is different. Yeah, go ahead. Um, in general, I would say you should just leave the bias on. I don't think that there's much reason to have it off. Um, it does cost you an extra parameter, but in general, it's not going to hurt anything. So I would just typically leave it on.
Yeah. So, like a counter example I can think of is there was a research paper where they said instead of representing all data as points in a vector space, we want to represent them as points on the unit hypersphere. So they're just directions. Okay. So it's not like we think of Cartesian coordinates, in 2, 3 dimensions. It's just a point in space. But here they're saying, no, everything is just on the surface of the sphere, and we're just going to do rotations to move things from one place to another. So if you're just doing rotations, then there's no real need for a bias. So that would be like a specific research paper I can think of. But yeah, it really boils down to if you are thinking about what the internal representation is, if you know that it can't, like they're in that toy example, they're saying that the lines could be different angles, but they all had to go through the origin. So if in your problem, the way you formulated it, everything goes through the origin, don't use bias. And that's what Ryan said is accurate. That's relatively uncommon. Usually people are just like, I don't know what this is. This is just a 128 dimensional space. So if you don't know, then it's safer to set the bias on. And the model can always choose zeros for the biases. It doesn't have to use them.
Okay. Um, so looking at the sequential, like I was mentioning, it just passes things forward, so you don't have to manually call everything. So you could alternately say, define this linear layer, pass it through the linear layer, define this ReLU, pass it through the ReLU. But it's just kind of a waste to have that many lines of code when you're saying, I know that it's just going to follow through this sequence of layers. Um, so digging into the um, specifics of images, so like I mentioned, we have this very high resolution image. So it's 1920 by 1282, I guess, and it's got red, green, blue channels. This is millions of pixels. So like imagine here we only have 3 neurons. We would need 7 million neurons is what they're saying with it when you multiply all of this out. And so when you have that many neurons, it's very expensive to compute. And so what people have realized is we can just downscale these images and it makes it much more constrained and much more reasonable to process. So we can reduce it down to 224 by 224 is a pretty standard image resolution. A lot of models are trained at this resolution for classification. And then we've reduced the space by like a huge factor, but we can still tell it's a car. So hopefully the network that we train can also still tell that it's a car. So some people do that resize. Other people might do a center crop. So they say the most important thing is probably at the middle of the image. So you can crop it down and say, resize it 256, 256, and then crop it down to 192, for example, and we end up 192 per 192, and that ends up a much more manageable resolution. Um, we've talked about gradient descent a little bit. So this is saying now let's define a neural network that has this certain format. So we say that we need our input to be the number of channels, which is red, green, blue, the height to be 192, the width to be 192, and then we end up with this certain size linear layer going from there to some intermediate size. And then we might go from that intermediate size back down to 1 to make it so we have some final prediction of how expensive the car is. Um, so this is them showing how you actually apply the weight updates. I don't think it's super important that you understand this because this is something that's just automatically done by PyTorch. You don't need to do the gradients and the weight updates by yourself. So typically you don't have to deal with this, but this is them showing an example saying, here we have the parameters, we push in the direction of the gradient by the learning rate a little bit, and we just update our weights little pieces, and they're showing, okay, we just go up the hill, go down the hill in the direction that we're trying to go. So that's the actual details of it. But in reality, typically what you do is you just use an existing optimizer from PyTorch. So this is stochastic gradient descent. So you just import this and you say, use that. I don't want to do all of the weight updates by myself. So here's the example showing the optimizer. So you say, I want the optimizer to function on top of this set of parameters. So I define this model, optimize just this model. And then we measure how good the model is, and then we move in the direction of the gradient. So we say, okay, when we did these operations, we moved in a certain way, zero it out, and then move backward in the direction to learn the relationships that we're trying to learn. So learning rate is very important. I saw someone in the chat mentioned, like, if your model's not learning, maybe your learning rate is too high. So here's an example of that. So if it's too high, you might end up taking steps that are too far, and then you kind of exit your hill instead of going down it. If it's too small, then you end up taking a million tiny little steps and you're just moving very slowly. And if you choose a proper learning rate, then you'll end up taking a decent number of steps in the right direction. So now there's a whole section on matrix multiplication. We're already a little bit over, so I'll just kind of blaze through this. If anyone has any questions or sections they want to touch on, feel free to guide that now. Otherwise, I'm just going to blaze through. Yeah. A lot of that is just from experimentation. So in general, it depends on the complexity of your problem. In reality, you typically don't need that many layers. Most people don't have so much data or such a complex problem that they really need a ton of layers. So you have a couple different things that you can impact there. So you can say the number of layers, but then you can also say the number of intermediate neurons. So you can say I have 2 layers, but one of my layers is 4,000 neurons or something like that. You can represent many relationships inside of that one single layer. So I would say in general, it's kind of just in most problems, it's custom enough that you have to say, I'm just going to experiment with this amount and try some different things and understand, do I need more layers because it's a complicated thing, or do I need less because I don't have that much data? But in a lot of things, you will start with some existing network that already does what you want. So like for image stuff, people have already figured out, here's a good layout of layers in order to do image classification, for example, and you can just use that. So you don't have to actually do the figuring out of how many layers and how many neurons and what configuration. Yeah. Okay. Yeah, so going on to the next section, so just matrix multiplication. So you can do this very easily with PyTorch. So we've shown you can do the NN layers, and that will automatically be doing some matrix multiplication for you, but you can also do things manually. So if you say, I want to make some, I invented some crazy new layer, you can say, okay, do matrix multiplication in this way, and then do this, and then do that. So this is basically saying we have some input, we have some weights, we've just randomly defined this weight matrix, and then we multiply it by our inputs. Um, so you can do matrix multiplication like that. And so one of the things I was saying is you have to keep track of your dimensions and everything. It's more of a big deal if you're doing it manually by hand. A lot of the layers will kind of magically do some tricks in order to make sure you're in the right direction. But if you do it by hand, you have to make sure, is it weights first or is it input first, or which direction is it? So I mentioned adding nonlinearities. ReLU is a very common one. You might use a sigmoid or something else like that. Um, and so what I was mentioning before is if you use no nonlinearities, no matter how many layers you do, you're still going to end up with just this kind of triangular cut pattern. If you add nonlinearities, then you can do deeper and deeper relationships, and you can do the sort of curved patterns. So here's a list that they've given. That's a bunch that people use. That's another thing that you might want to optimize for. So you can do the number of layers, you can do the size of the layers, and you can also change the activation function, and that might have impact on your model's performance. So we showed some website that lets you kind of practice and visualize matrix multiplications. I'll just skip past that. And that's the whole 2 workshops. Any questions? Okay, thank you.
Awesome. Thanks, Ryan. All right. So two quick administrative notes. So regarding this series, so we're combining the textbook, the computer vision textbook, with this practical computer vision series. So if you're someone more similar to me that's ever done Kaggle or played with deep learning, then some of these things may have been familiar. You may have seen PyTorch before. We introduced a few libraries, so most people will have had at least some exposure to NumPy, but maybe not Pillow if you haven't done images before. If you are somebody who's actually done a lot of work with images, but you come from like a computer vision background or like a computer graphics background, then this stuff with PyTorch and whatever might have been very new for you. So next week we're doing the textbook. Sorry, next session. It's not next week. Next session. And the first few chapters of the textbook have a more theoretical foundation, and the script is going to be flipped. So I do not have a computer vision or computer graphics background, and almost everything in chapter 2 is new to me. So at the beginning, we asked how many people have looked at the material. It's possible that there's more material in chapter 2 than there is time to go through all of it. So I recommend, even if you don't have time to really read through, at least skim through chapter 2 and see what the topics are. Because basically, like, I got one paragraph into chapter 2 and I was like, wow, here's something that's completely new to me already. And so we can spend some more time talking about like some of the, to get intuitions around like, well, what is this, homogeneous projective geometry stuff that I've never, ever, ever seen, no matter how many like, computer vision, you know, classification, detection, segmentation, all that stuff. And I've never seen this stuff before. So then the flip side is if you're somebody who comes from a computer vision background, you might be like, yeah, and like find that chapter's a lot easier for you than this stuff was. So that's the first administrative thing. The second thing has to do with timing. So we actually are going to be taking the next 2 weeks off. So Next weekend is 4th of July weekend. It's the long weekend. The 4th is, I think, Friday, and then we have a long weekend. So we figure a lot of people probably would like to have plans and take that off. And then just there are conflicts the following week. So the next session is actually going to be July 19th. It's going to be in 3 weeks. Um, so you have a little extra time to do the reading, look at the materials, whatever. So I'll announce everything and I'll put stuff on Slack for this particular series because we're going back and forth and there's all these different workshops and the chapters, whatever. Probably would be helpful if you haven't yet joined Slack just to be able to keep track of like what we're covering. So I think that's it for announcements and thanks for joining us.